Tonight what we're going to be learning about are these things called intermolecular forces. We'll also be talking a little bit about intramolecular forces and the difference between the two. So there are two types of forces that we deal with in chemistry. One is intramolecular forces and the other is intermolecular forces. And we're going to abbreviate the intermolecular forces as IMF. Okay, even though you could abbreviate intramolecular forces as IMF, they don't. They say that for the intermolecular forces. Intramolecular forces are the force that keeps molecules together. What we know them as in chemistry and in this class is bonds. So these are the bonds. So an intramolecular force, if you think of an intrastate or an interstate, interstates are highways that go between multiple states. An intrastate is only a highway that is found within the single state. Okay, so an intramolecular force are the forces that are found within one molecule. And what are those? Those are bonds. So if you look at the image on the right, okay, you have these guys are your intramolecular forces. And what this picture shows is that it takes energy to break these bonds, okay, because they have some sort of attraction to each other. So in order to separate it, it breaks the bonds. And notice that this guy to separate is 415 kilojoules per mole. Just look at the number right now. Okay, so we're comparing 415. Now, intermolecular forces are the forces that attract molecules to other molecules. And this is actually the force or attraction that keeps different stages of matter together for solids and liquids. Okay, so that's what when we were talking about our heating curves, like this part, when they're undergoing the phase change and they're separating and they're breaking apart their attractions, we are breaking apart the intermolecular forces during this part of the graph when you are undergoing a phase change. Now, if you compare the energies that are used to break these forces or attractions to one another, you notice that the bonds has 415, and for the same molecule, just to separate them, you have 41. So you're talking about it's 10 times greater, the bonds that hold the molecule together, than the attractions that hold molecules to other molecules. So it's extremely, even though they're present, it's not as strong as the bonds themselves. All right, so let's focusing on intramolecular forces for a minute. Types of bonds. There are 4 types of bonds that you're going to have to know, and these are in order of strength. So when you increase your strength, you increase their melting points and boiling points and everything like that. Okay, so they're more attracted to one another. They have a lot more energy associated with them, I guess you would like to say. The first is network covalent. That is the strongest by far. Then you've got your ionic, then you've got your metallic, and metallics are only just like metals, and then you have your covalent compounds, which is where you share them. Network covalent. So a network covalent is a covalent compound where they are sharing those electrons. So you're like, wait, how can it be covalent is the least, but network covalent is most? Well, what happens is these are very special ones. And what they are is they form this continuous network of covalent bonds where they're all interlinked together. It's really not one individual molecule. So even though we write it as like SiO2, okay, for silicon dioxide, which is sand, what's happening with these is that they're actually they are connected. All silicons and all double oxygens or 2 oxygens are interconnected with other SiO2s, and you get this looking structure. Notice that there's really no way that you can tell where one ends and one begins. Another example, and these are all examples that you're going to have to memorize, is diamonds and graphite. These are your carbon-based ones. So diamonds, if you look at this structure, okay, and then we've got graphite with just this structure. This is one layer of graphite, and so if I looked at it like this and flipped it on its side, that's where it'd be. And so when you're writing with a pencil, what you're doing is you're actually ripping off each layer of these little graphite layers. So after that one's gone, then now I'm writing with my pencil, and then I get that one off. Okay, but they come off strip by strip is what you're doing when you're writing with this network covalent of graphite. Diamonds, if you look at that, that is really intensely interworked together. It seems very similar to the silicon dioxide as far as structure goes. And when you look at these are extremely hard to break, and that's why diamonds are so strong and sand is so strong, and so they have such high melting points. But you do need to know that anything with silicon is going to have a network covalent bond, and anything that's the 2 that are carbon-based, diamond and graphite, you have to have memorized that those will have network covalent bonds. All right, the next strongest is your ionic bonds. And ionic bonds, as we've already talked about in the past few chapters, is that where they give and take electrons. So if you give and take electrons, this forms a really strong attraction to one another, and it's made up of the metals and the nonmetals. So what happens is you've got all of these examples, these are compounds, and if you look at your first element, once again, it will be a metal, and therefore it will have that ionic bond. But if we look at this structure to the right, what you're noticing is that all the negatives are, well, let's, I guess, focus on more of a positive. So if you look at the positive, it is surrounded by 4 different negatives that we see. There's also one going to be like right in front that's covering it, and then there's going to be one behind it. So it is surrounded, the negatives are surrounded by the positives, and the positives are surrounded by the negatives. So that forms an extremely strong attraction because they are fully positive and negative charges, not just like a little partial with like the polar bonds. Metallic. The metallic bonds, how do you identify a metallic one? It's literally any metal. So if you see it on the periodic table and it's written by itself and it's a metal, then it's going to have this metallic property. They always use this word of sea of electrons. Well, what happens with this metallic type of bonding? Well, if you have your structure, what happens is that the valence electrons from metals are so weakly bound to the nucleus that they roam around freely among the whole metal. So it's really not the electron is stuck to your individual element at all times. It literally is kind of like flowing throughout. If you can see this and try to imagine, it's like literally flowing out. No electron, if you look at this, it's not very structured, but it forms a sea of electron where they're constantly moving. That's why metals can conduct electricity. Electricity is the flow of electrons, and so metals can conduct because these electrons are able to move freely throughout the whole thing. Okay, so metallic has a sea of electrons where these electrons can kind of hop from nucleus to nucleus and it's like delocalized totally. All right, then the last one of type of bond is covalent, and as we talked about, this is where you're sharing, and it's made up of 2 nonmetals. So where do we see these? If you look at this is where they're sharing. That's where we had those Lewis dot structures of them sharing these bonds right here. All right, so covalent bonds are the weakest because they're sharing these electrons. They don't have that full charge and everything like that. All right, so in summary, we've got ionic, covalent, metallic, and network. How do you identify them? Well, you can identify them based off their boiling points, melting points. Covalent by far and away has the lowest of all of them, and then network has the highest of all of them. The only one that can conduct is when you are allowed to move electrons, and the only one that allows electrons really to move is metallic. Now, with ionic compounds, if you dissolve it, it does the very similar process of the metals, where these electrons are able to flow. So that's the only time ionic compounds can do it, is when they're dissolved in water or molten, which means in the liquid state. But as a solid, they cannot conduct electricity. The metallics can always conduct. So how can you identify them? Ionic, you're just going to look for that first nonmetal, or to be a metal, the first element to be a metal, then it's going to be ionic. For network covalent, you're going to look for that diamond, you're going to look for anything with silicon, you're going to look for that graphite. Metallic, just look for anything that's a metal all by itself, by its element, and then covalent, you're going to look for the first element being a nonmetal. All right, so now to move on to intermolecular forces. Remember, intermolecular forces are the forces that are between 2 different molecules. So intra is the bonds, so it's the forces that keep a molecule together or compound together. Intermolecular forces are the attraction from one compound to another compound. There are 4 types of IMFs, and these are also listed in order of strength: ion-ion, hydrogen bonding, dipole-dipole, and London dispersion. This is the primary part of this unit that we'll be focusing on, so it's really imperative that you listen and understand how to identify which type of what type of intermolecular force a compound would show. So ion-ion. Ion-ion is the strongest of all IMFs, and what it is the ones that will exhibit this are the different ionic compounds. So it's an attraction also between the charged particles, but how you identify it is you literally look for if it's an ionic compound. And the reason why it's the strongest, once again, it's these interactions. So if I were to, let's just outline one sodium chloride, okay, and I'm going to outline another sodium chloride. Notice that these two would be right here, would be the attraction, and you have a negative directly attached to a positive or in a very near vicinity, so it's going to be a very, very strong attraction. So this would be the most attraction. So once again, how you'd identify it is you just look for an ionic compound, and that'll have ion-ion interactions for IMFs. Hydrogen bonding is for covalent bonding. Now, every other one after this is always going to be for your covalent compounds. So there are 3 different types of covalent compounds. There's hydrogen bonding, there's dipole-dipole, and then there is going to be London dispersion. So this is the first type of covalent. So after you're done identifying all your ionics, now you're going to look for your covalents. And this one is a very special type of IMF. It is not really a bond, even though we say it's hydrogen bonding. What it is that it is where a hydrogen is directly attached to any of your fine elements. Now, the H has to directly be attached to an F or N. So if I had like a C, C, O, and like let's say an H over here, this one would not exhibit hydrogen bonding because that is not directly bonded. But when we look down here, if I look at that oxygen is directly bonded to a hydrogen, that is going to exhibit hydrogen bonding. Now what happens with hydrogen bonding is that because these elements F, O, or N are very electronegative, they tend to draw within that polarity bond, the polar bond, they tend to draw a lot of electrons. So this is extremely negatively charged. Okay, I'm going to make that red because I like red to exhibit the negatives. Now, hydrogen at this stage, because these guys have really taken away all that negative, that hydrogen is extremely relative compared to other types of covalent bonds, is a lot more positive than usual. So therefore we've got this larger slightly positive being attracted to this larger slightly negative than normally is exhibited between any covalent bond. So because we've got that, these guys, we have a positive with a negative, they're going to be more strongly attached. Now because it's only partial, that's why hydrogen bonding is not as strong as ionic, where it's completely charged, where you have a definite positive and a definite negative. This just has a partial positive and a partial negative end. All right. Dipole-dipole. Dipole-dipole, how do you identify it? It's between polar molecules. So it's very similar to that hydrogen bonding where you have a slightly negative and a slightly positive end, and then they're going to be attracted to the slightly negative and slightly positive end of another compound. Hydrogen bonding has this extreme. Polar bonds also have it more extreme than when you don't have it. So if you look at this, the negative end of a polar molecule will be attracted to the positive end of another polar molecule. So how do you identify one that will have a dipole-dipole? They will have an N, they will be a polar molecule. So going back to last chapter, if you have NF3, you're going to have a polar molecule because it's got that trigonal pyramidal shape, and so it's going to be polar, and therefore all you have to do is it's going to have this dipole-dipole. What does dipole-dipole mean? It says that it's a compound that has 2 poles, meaning it's polar. We've got a positive pole and a negative pole, and it's attracted to something else that has a positive pole and a negative pole, so one 2-polar system. All right, the last one is London dispersion, and this is where you have temporary dipoles. Okay, so this is between 2 non-polar molecules. So typically they don't have a polar connection. They don't have poles. Okay, so we would say that they are non-polar molecules. This is how it happens, though. It doesn't happen the entire time. It only happens for a very short time. So actually, instead of O2, I'm going to focus on hydrogen, which is right over here. All right, so typically what happens is when you look at this, and this is like your electron distribution, it is perfectly even. But because electrons are constantly moving, okay, they're constantly moving, at one particular time, because they're constantly moving, at one particular time there might be more electrons on one side than on the other. When that happens, this side will have a slightly negative charge compared to the other side will have a slightly positive. And it's only temporary because they like to be distributed evenly, but it's not like they're just constantly moving. So at some particular time, there's a good possibility that there will be more electrons on one side than on the other side of the compound or the molecule. So at this point in time, what happens is that the electrons on this hydrogen are like, wait a second, we're distributing, but now I see this positive over here. And they're gonna be like, wait, I loved by positive. I love positives. I'm negative. I want to be by that. So what they do is they shift. And what happens is we get this shift of these other electrons, which is induced. It's induced because we kind of force these electrons to want to go over there. And what's happening is that these electrons are now here. The positives of this guy are now attracted to the negatives of that guy. So the positive charge is kind of attracted to the negative. Now, this is not how they actually like to exist, but it is only at this moment that the attraction occurs. Not at any other moment is there an attraction between these, because you have a zero charge and a zero charge. That is never going to get an attraction together. It's only at this point in time where they have a negative and a positive that there will be any sort of attraction to one another. So this is the attraction right here. And then what's going to happen, though, is they're not going to like that, so they're going to go back to this pretty fast. Okay, so this is a very short attraction when it exists here, and that's only because of electrons move, and at some point it's going to be heavily on one side versus the other just by chance. All right. So in summary, we have 4 different types of IMFs. How do you identify them? Ion-ion, you're going to look for ionic. It is the strongest one, and an example would be NaCl because it is an ionic compound. The second one, these are all covalent bonds. Okay, so the second strongest will be this hydrogen bond. Once again, it's not literally a bond. It's still the attraction between the hydrogen of one compound and the F, O, or N of another. But in order for it to have hydrogen bonding, the compound has to have a hydrogen directly bonded to that F, O, or N. So an example would be water, because that hydrogen is directly connected to the oxygen. The third one is dipole-dipole, where you have 2 poles. So this is between polar compounds. An example would be NF3. And then the last one is London dispersion, and this is between nonpolar compounds. This is the weakest by far, and an example would be any nonpolar compound, such as F2. Hopefully you kind of have an understanding. This is a really good chart on how to be able to identify them, what type of IMF they would have, and we will be discussing this more soon.